Mathematical induction is a procedure to prove mathematical statements for all natural numbers. It has 3 steps. Let's see the first step. It is to show the statement is true for 1. Then our second step is we assume that the statement is true for some natural number k. We call this assumption as induction hypothesis. Then our third step is to show that the statement will be true for the next natural number, which is k plus 1. Now let's see our first example, and hopefully by the end of this example the steps will be more clear to you. Our task is to prove that 1 cube plus 2 cube plus 3 cube plus n cube equals n squared times n plus 1 squared over 4. Now let's refresh what were the steps again. Our first step is to show that for 1 the statement is true. Second step, assume that the statement is true for k. And the last step is to show that the statement will be also true for k plus 1. The first step is the easiest. We need to substitute 1 into n. On the left hand side we get 1, since 1 cube is 1. On the right hand side we get 1 squared times 1 plus 1 squared over 4. On the numerator we get 4. 4 over 4 equals 1. Therefore, we've shown that for n equals 1, our statement is true. Now we need to assume that the statement will be true for k. So we will get this statement, this equation, in the second step. On the next slide, I will show you how to do the third step. We will have to show that our statement is true for the next natural number, which is k plus 1. So this means on the right hand side we will have k plus 1 squared times k plus 2 squared over 4. If we substitute k plus 1 into the place of n, then we will get this, and here since we have n plus 1, k plus 1 plus 1, it will be k plus 2. So remember, this is what we would like to see on the right hand side. On the left hand side it is quite straightforward. Our last term will be k plus 1 cube. So let's see what equation we've got from the previous step. Here, this was the statement from step 2. Now let's see, we need to have k plus 1 cube on this side. So to get this, we will add k plus 1 cube to both sides. And from this stage, we're not going to add or subtract anything from this equation. We will only rearrange this right hand side and see if we can get what we would like to see. So first of all, I'm going to move this into the numerator by multiplying this by 4. Okay, and then the next step is, we notice that here we have k plus 1 squared, and here in the second term of the numerator we have k plus 1 cube. This means that k plus 1 squared is the greatest common factor of these two terms in the numerator. So I'm going to factor this sum, and if I bring outside k plus 1 squared, I will end up with k squared from the first term and 4 times k plus 1 from the second term. Here we go. Now let's see what can we do. Well, we need to expand this inside the bracket, so we will get 4k plus 4, and of course this k squared. So here we go, k plus 1 squared times k squared plus 4k plus 4. Now, if you recognize this, I hope you do so, this is a perfect square, so we can factor it. This will be the square of k plus 2. Since our last term is 4, so that's the square of 2, and 4k will come together as 2 times k times 2. So therefore we can change this to look like a square, a perfect square. So here we go. On this left-hand side, we use the same as we've got from the first row, and on the right-hand side, we ended up with the expression we wanted. So therefore, it means this statement will be true for all natural numbers. And now this is your time to practice. Prove that 1 squared plus 2 squared plus 3 squared plus n squared equals n times n plus 1 times 2n plus 1 over 6. Remember, in order to prove this statement, you have to follow mathematical induction. Please pause the video now, try to work out this proof, and then once you have it, continue with the video to see the answer. First step is to show for 1. Second step is to assume it's true for k. And then the last step is to show it's true for k plus 1. This is our aim on the right hand side. And then we were going to use the same idea as we did in the previous question. We simply add k plus 1 squared to both sides on the statement in step 2. And then rearrange this right-hand side. And since we received the same fraction as we wanted to get, it means that the statement is proved. Step 3 is proved. Therefore, our original statement is true for all natural numbers n. Now let's see our second example for mathematical induction. This time our task is to prove 8 to the power of n minus 1 is divisible by 7 for all natural numbers n. First of all, my question is, how can we show that a number is divisible by 7? Well, if a number can be written as 7 times an integer, which means any whole number, then the number will be divisible by 7. We're going to use this idea in our steps. Let's see our first step. I hope you remember. Our task is to prove that it's true for n equals 1. Now let's substitute 1. 8 to the power of 1 minus 1 equals 7. Now, is it divisible by 7? Well, of course it is. 7 could be written as 7 times 1. 1 is an integer, so it means 7 is divisible by 7. Let's see what is step 2. We need to assume that our statement is true for a number k. This means that 8 to the power of k minus 1 is divisible by 7. How can I use this information to write up an equation? Well, it means that 8 to the power of k minus 1 can be written as 7 times an integer. This is what I'm going to write up. Equals 7r. I'm going to use this r as an integer, which I don't know. In step 3, I need to show that the statement will be true for k plus 1. So what I need to decide is that 8 to the power of k plus 1 minus 1 is divisible by 7 or not. I'm going to use the statement from the previous step. So I will start with the statement of 8 to the power of k minus 1 equals 7r. Now my aim is to see 8 to the power of k plus 1 minus 1 on the left hand side. Before I could get 8 to the power of k plus 1 instead of 8 to the power of k, I will move my minus 1 on the other side. Now I only have one number here, one exponent here, so I can make some changes in order to get 8 to the power of k plus 1. Now if you think of the rules of exponents, I hope you remember the product rule of exponents. So to get plus 1 in the exponent, it means that you need to multiply this 8 to the power of k by 8. And that's what I'm going to do on the other side as well. Now here on this side we will reach our aim, 8 to the power of k plus 1. On the other side we need to expand the bracket, so we will get 56r plus 8. Now I'm almost there with the left hand side. I'm only missing this minus 1. How can I get that? Well, we need to subtract 1 from both sides. So here I will get what I wanted, and here I simply need to reduce this 8 by 1. So therefore I will get 56r plus 7 on the right hand side. On the left hand side I finally reached my statement, the left hand side of my statement. Now let's see if this expression 56r plus 7 is really divisible by 7 or not. Well, if it can be written as 7 times an integer, then it is divisible by 7. Since I realized that 56 can be written as 7 times 8, 7 can be written as 7 times 1, I can factor this expression. So on the right hand side, I will get 7 times 8 times r plus 1. How do I know whether 8 times r plus 1 is an integer or not? Well, I remember r was an integer. 8 times an integer is still an integer, plus 1 is also an integer. So therefore I proved that 8 to the power of k plus 1 minus 1 is divisible by 7. Now what does it tell me? It means that my original statement, 8 to the power of n minus 1, will be divisible by 7 for all natural numbers n. And now this is your turn to show that 7 to the power of n minus 1 is divisible by 6 for all natural numbers n. Please pause the video, and once you have your proof, please press play to check your answer. Remember, the first step was to prove for 1. Our next step is to assume it is true for k. And our next step is to show it is true for k plus 1 as well. Let's see if it's true. We're going to use the same trick as we did in the previous question. I hope you had it right. Well done for it. Now we know how to prove statements by using mathematical induction. The second part of this video is to disprove statements by finding counterexamples. You are already familiar with counterexamples from previous grades. Our task is here to disprove the statement that 2 to the power of n plus 2 times n to the power of 2 is divisible by 4 for any natural numbers. This means if we find one number where the statement is false, well, we disproved the statement. So our only task is to test random values and find one where the statement is false. I'm going to arrange this data into a table. I'm going to use one column for the values of n, one column for the values of this expression, and I will be able to decide easily whether the solution is divisible by 4 or not. I'm going to try with easy numbers. So I'm going to try with 1 first. If I substitute, I get 4, and I realize it is divisible by 4, so the statement is true. Let's try 2. My result is 12, and well, this number is also divisible by 4, so I say yes. Let's see number 3. I will substitute and I will get 26. Is it divisible by 4? No, it is not divisible by 4. Therefore, I disproved this statement above. So we can say 3 is a counterexample for the statement. Hence, our statement is disproved. Now it is your turn to find a counterexample to disprove this statement. Please pause the video, and once you have your counterexample, you can press play to see the answer. And the answer is, well, here again we need to use a table to organize our data. I'm going to use 4 columns this time because I want to have a column for values of n. I need 1 column for the left-hand side, 1 for the right-hand side, and the last column is to decide whether these two are equal or not. And let's test our values. Start with 1. That's equal. Then continue with 2. And that's also equal. And continue with 3. We notice these are not equal. You might find different numbers for counterexamples. Number 3 is not the only counterexample you could find.